So the forebrain and subcortical structures. So in this case, we're going to be talking about these colored in pieces here, all kinds of good things. We're going to start, let me diagram some of these for you. The forebrain, the hypothalamus. Remember we talked about the hypothalamus, right? What was the hypothalamus involved in with our zombie? Always hungry. Basal ganglia are going to be involved in movement. Thalamus is going to be involved in kind of switchboard stuff. The hippocampus we'll be talking about. And the amygdala, which was also involved in our zombies always being what? Emotions, being mad, being angry all the time. So let's go ahead and walk through these a little at a time. And I don't know why that always ends up over there. There we go. So the amygdala is this green piece underneath the crosshairs there. And so it's not very small. It's almond shape, and that's actually how it got its name. Somebody thought it looked like an almond. It's involved in fear responses, emotional processing, and some types of learning. Now, one of the things that makes understanding brain function hard for somebody in your shoes, somebody just getting started learning about the brain, is so I say something like learning. And almost every structure ends up being involved in learning. And the reason for this is all these pieces of the brain work together in concert so that we have the experience that we do. My analogy would be like if you went to hear a symphony. You can imagine you've got the flutes, they're doing flute stuff, and you've got drums doing drum stuff, and whatever the sax people are doing, I don't know what they do. But anyway, so you have all these people who are doing these parts that independently might not sound like much, but when you bring them all together, you get a symphony. It takes on a very different aspect. Well, that's what's going on in the brain. We have all these parts. So how is the amygdala with fear involved in learning? What would you think? I'm sorry? Okay, it adds what we call emotional valence. It adds information. It's like having that anxiety we were talking about. Anxiety is a good thing. It helps you to figure out what's important so you can learn things. Things with low emotional valence aren't that important. Things with higher emotional valences are. There's, just like many of these other structures, there are things that can happen to the amygdala that give us problems. One is called the Kluver-Bucy syndrome. In the Kluver-Bucy syndrome, what happens is the amygdala gets damaged. And if you have Kluver-Bucy, a couple interesting things happen. One of which is you lose your fear response. Things that might make you scared don't particularly bother you. People with Kluver-Bucy will approach strangers much more rapidly than you or I. They won't go, is this person a threat? This kind of stagger on into it. The other thing that's really interesting, which I can't tell you why this happens, but it does with this, is people with Kluver-Bucy and animals with Kluver-Bucy become hypersexual and non-discriminate in terms of what they will partner with. And that species, inanimate objects, it doesn't really matter much. They become kind of hypersexual in that manner. There's another disease that you may have heard of recently, because it's been in the news a lot, toxoplasma gondii, I think is what it is. It's a parasite that is life cycle goes through mice, rodents, and other rodents, and cats. And what it does, this parasite, is it attacks the amygdala in the mice. And if you're a mouse with no amygdala, cats don't bug you that much anymore. They don't bother you. What do you think happens then? You become dinner. And guess what? Now that parasite has made its way all the way back to the cat. The cat eats the mouse, passes on that parasite through its urine and feces, where the mice pick it up in the next generation. It also attacks the amygdala. Just behind the amygdala, in the purple section here, the amygdala, I'm sorry, that's amygdala, this is purple part's the hippocampus. Hippocampus is what was removed in the guy I just told you about, Henry, who lost his ability to form new episodic memories. It is a structure deep in the medial temporal lobe, so the middle of the temporal lobe. The temporal lobe, if you look at the brain from the side, there's this part that kind of looks, if you think of this as like a boxing glove, the thumb would be the temporal lobe, this piece down here. Definitely important for episodic memories. So stories about who we are. If you drove in today and you can remember where you parked your car, that's an episodic memory. If you remember high school graduation, that's an episodic memory. If you remember how to tie your shoe, that is not an episodic memory. That's a procedural memory. It's how to do something. It wasn't until H.M. had his real problem that we knew that there were different kinds of memories. So hippocampus is very important for all those things. Also spatial navigation, being able to move in space, having spatial maps. So what do I mean by that? Suppose you wanted to go to Faulkner University. I don't know why you'd want to, but you might want to. Who could get there? Not very many of you. Okay, some of you. All right. Now, how would you go? You said you could get there. How would you go there? You're right here. Okay, what if the interstate was closed? Spatial maps. Having the ability to plan alternate routes, that's because he has intact spatial maps. London cabbies have larger hippocampi than the normal person. And it's because, what you have to understand about London, London's streets were laid out back when ox carts were like the modern transportation. Narrow streets, kind of willy-nilly where they go. Not laid out in a grid pattern. So if you're a cabbie in London, you've got to learn all these funky rules about how to get where you're going, where things are hidden. Through experience and learning all things that a London cabbie has to know, their hippocampus actually grows larger than a normal person's. I think that's kind of neat. Let's see, what else we got over here? Oh, here's more stuff on HM. So Henry Molson, we can use his name now because he died a couple years ago of old age. These are all things that conditioned learning that was not affected with him. We'll talk more about that in a coming lecture, in a coming chapter, the different types of learning that are possible. But important things going on down there in the temporal lobe. And it's not surprising that the amygdala and the hippocampus are right next to each other. They're connected to each other because that fear and anxiety is such an important part of our learning. Now, what's interesting is this. If I give you a learning task, I give you a list of 20 words to learn, and there's no punishment involved, no reward involved, you're not going to learn it that well. But if you know I'm going to get out my taser and zap you. Yeah, so you'd like, okay, I'm going to pay attention. If you're going to get tased every time you get one wrong, suddenly the emotional valence goes up. You become more attentive. And that's exactly what we find happens. Now, conversely, what also happens is if you take anxiety too high, that will block learning. So if I hit you too many times with the taser, then you won't learn, but it'll still be hysterical to everybody else. So it'll be worthwhile. So that's all things going on there in the hippocampus. The hypothalamus, again, it's going to regulate a lot of motivated behaviors, such as sexual desire and all that. Regulation of body temperature, blood pressure, blood glucose, many, many things going on with the hypothalamus. I'll give you a moment to catch up with that. And we go to 1:30, is that right? No? Oh, okay. You already didn't make it. All right. Moving on. This bluish structure up here is where we're headed next. The back part of the curved part is going to be the fornix, but moving forward, we're going to get into the basal ganglia. The basal ganglia are important in the production of planned movement. So if you have somebody with Parkinson's disease, this is going to be the area that is affected. Huntington's is also a disease that affects that area. There's a structure up in that area called the nucleus accumbens that's going to be important to us this semester, so it's worth remembering. It's involved in the reward of behaviors and wanting of behaviors. It's an internal reward system. It's involved in wanting. So if you are like a sports player and you've been working, say, on your golf swing, and you get the golf swing perfect and everything's just right, and you feel real good about that, that is the nucleus accumbens firing. When you have romantic relations with someone, that is the nucleus accumbens firing. When you are taking heroin, that is the nucleus accumbens firing. And now here's a fascinating little fact for you. I think we have a few more minutes. Your brain on heroin, if you inject heroin, we put you in a functional MRI, we'll see what your brain looks like, what part of your brains are lit up. If you are in love and we put you in a functional MRI, the same areas of your brain are lit up. Because what's going on with the drugs of abuse is they're lighting up, they're short-circuiting the process to reward. So you don't have to go through the effort of doing something to get the reward. So in this respect, being in love is much like being on drugs. And it should explain much of the behavior that you see in others and maybe even in yourself when you're in love. So on that happy note about love, I will let you go.